Okay, let's begin. The topic of this video is going to be solubility equilibria as governed through solubility product expressions. Solubility product, simply stated, is an equilibrium constant that describes the solubility of a substance. A sparingly soluble salt, as your instructor may describe it as. Basically, for a reaction such as this one, in which an ionic compound that is a solid is dissolving in water, we can write a reaction that describes the process of dissolution as an equilibrium. In this equilibrium, what happens is ion A and B, that's the cation and the anion, respectively, the positive and negatively charged ion, will essentially hydrate or become surrounded by water molecules to yield ion A and ion B. And again, in my representation here, A is the cation and B is the negatively charged anion. Of course, when they dissolve into the water and are surrounded by aqueous, or are surrounded by water molecules, I'll yield X copies of A, given the subscript here, and Y copies of B, given whatever subscript this is here, to balance the ionic compounds formula. So for this event, we can describe it as an equilibrium. That is a process by which dissolution occurs, and the reverse process, that is formation of a solid, also occurs simultaneously, crystallization. That equilibrium position can be described by an equilibrium constant called the solubility product, Ksp. We define Ksp for a sparingly soluble salt as through this equation, which is typical. Square brackets A, square brackets B, they're multiplied by one another. However, before we do the multiplication, we raise A to X and we raise B to Y, where X and Y are the numbers in the balanced chemical equation. So that's the solubility product. That's how it works. The solution is said to be saturated when no more of the substance can dissolve. Note that in our K expression, we don't have a term for this on the left, and that's because it's a solid. We assume its activity is unity, and it doesn't show up. You probably have seen the K expression before. To refresh your memory, I'd like to go through and work a few problems so we can see this in action. These types of problems are reasonably important. You could expect to see one on an exam in some way, shape, or form. Usually, even the end of semester exams will test concepts related to solubility. So let's just dive in to our first problem type. This one's actually probably going to be the easiest that we'll do in this video, but it's predicting something called molar solubility in pure water. Okay. Lead iodide has a pretty yellow colored compound. It's got a Ksp of that. What is the molar solubility of the lead iodide in pure water? Well, if I'm tackling this problem, the first thing that I want to do is write down a balanced chemical equation for the dissolution of the lead iodide in water. That's a very important step. That's what I've done right here. So when the lead iodide dissociates and the ions become hydrated, or they become passed into the aqueous phase, I'll get one copy of lead 2+, aqueous, surrounded by water molecules. That's what that means. And I'll get two copies of I-, aqueous, or surrounded by water molecules. So it's a 1:2 ratio. So I've written my balanced chemical equation. The next thing I'd like to do is define my Ksp expression in terms of the concentrations of these ions at equilibrium. I've done that here. I've written that Ksp is equal to this value. That's the tabular value for the dissolution of this sparingly soluble salt. Other salts will have different values. This one's unique to lead iodide. That has to be equal to the concentration in moles per liter of lead 2+ times the concentration of I- squared. It's hard to see that 2 there, but there should definitely be a 2 because of this 2 here. So we've got to square the iodide concentration. Of course, the concentrations in these brackets here are going to represent molarities at equilibrium, or once an equilibrium has been established. So this number, Ksp, describes the equilibrium position. Now we've made some progress here, but we haven't really gotten a whole lot closer to answering the question, that is, predicting the molar solubilities of the salt in pure water. We can do this through embarking in what's called drawing an ice table, ICE. ICE stands for Initial Change in Equilibrium. We're going to use ice tables a lot in your class because they provide a systematic approach to problem solving. To build an ice table, what you do is you first start by rewriting the balanced chemical equation as I've done on the top line. Same as the one up here. Then I write initial change in equilibrium in the first column. This corresponds to our initial condition, the change that occurs, and the final equilibrium condition. For each of the reactants and products, I can then enter values into my ice table. For solubility equilibria, whatever is over here on the left of the arrows is always going to be a sparingly soluble solid. Consequently, we don't need to include any data in that column. But for other types of equilibria, it would be typical to include data here. Just for solubility equilibria, can we ignore this column? Makes it a little bit more convenient as it makes the math a little bit simpler. However, these aqueous ions we do need to include data for. We need to first start by thinking about the initial condition. What is the initial molarity of our ions? And what do we mean by initial condition? I like to think of it in these terms as the initial condition before any of our sparingly soluble salt dissolves. So are these ions present from any other source besides the dissolution of our sparingly soluble salt? In this particular case, they're not, because we're told pure water is essentially the solvent. So there's no lead or no iodide expected to be in pure water. At least that's what we assume for working this problem. Consequently, the initial molarity of each of those ions is 0. So in my initial entry, I need to write the molarities of the expected concentrations of these ions before any of my sparingly soluble salt dissolves. Now, I'm going to place the sparingly soluble salt in a beaker of this water. Some of it will dissolve, yielding lead 2+ ion and iodide. Now, I don't know how much will dissolve. I'm going to have to solve for that. But one thing I do know from the stoichiometry of the reaction, this being a 1:2 ratio, is that if I produce X of the lead 2+, I need to produce 2X of the iodide, because for every 1 copy of this, I make 2 copies of this. So get that from the stoichiometry, and that makes a lot of sense. Then, after I'm done defining my change, I define my equilibrium condition. My equilibrium condition is just the sum of the values above. So here it would be 0 plus X, or X. And here it's 0 plus 2X, or 2X. So these algebraic terms represent my expected concentrations of lead and iodide, respectively, once an equilibrium is established. Now, do I know what the concentration of lead or iodide is yet in molarity? Of course I don't, but I've made a little bit of progress, because now I know that this one should be twice as concentrated as this. And I also know something else that shouldn't be overlooked. I know that this Kx3 expression needs to be honored because it describes the equilibrium dissolution of this sparingly soluble salt. So what this number means is when this stuff dissolves to make a saturated solution, if I multiply the concentration of lead ion times the concentration of iodide ion squared, I got to get this number. Okay? So I know that this has to be true, and I also know that this ratio needs to be true. And I can use that to my advantage, because what I can do now is simply substitute in my variables from my ice table into my KSP expression. And that's what I'm going to work through on this slide. So I've rewritten that the KSP is equal to this value, the tabular value for this salt. It's also equal to the ion concentrations, this one squared, okay, multiplied together. And in this step, what I've done is I've substituted in the X for the lead concentration, and the 2x for the iodide concentration. I got that from my ice table. Note that I still square the iodide term. So if I square 2x, that gives me 4x squared, and multiply it by x, I yield 4x cubed. 4x cubed has to equal this number, because that governs the dissolution of this material. It's the number that governs the dissolution. So now I see I have an equation that I can solve for x. And this one's actually pretty straightforward to solve, because all I need to do is divide this number by 4, take the cube root. And when I do that, I find that x is 1.25 times 10 to the minus 3 moles per liter, or I can rewrite that as 0.00125 molar if you prefer to see it in that way. Now, why is this significant, solving for x? Well, if I look back to my ice table, I can see what x represented. X in my ice table, which I now know is equal to 1.25 times 10 to the minus 3 moles per liter, was equal to my expected equilibrium concentration of lead. And 2x, or twice that, which of course would be 2.5 times 10 to the minus 3 molars, would be expected to be my equilibrium concentration of I minus. So based on the systematic approach of using the ice table, I have been, in the KSP expression, I have been able to predict what concentration of the lead and iodide should exist in a saturated solution that was generated within deionized water, where no other ions were present. Okay? Now, a couple things about what we just did. This is a legitimate way to work a problem for dissolution of a sparingly soluble salt in deionized water. It's probably the easiest problem type. But there are a few things that you need to know. This KSP value, for instance, is temperature dependent. It's usually associated with a particular temperature. If you change the temperature, that'll change. If other ions are present in the beaker in which this is dissolving within, it's also very likely the solubility will change, because what can happen is ion pairs can form in solution, and that can have dramatic effects on solubility. Generally, we increase the solubility of ionic salts in such cases. So there's always sometimes a chapter on something called activity in your analytical chemistry textbook or quantitative analysis textbook. And when you get to that chapter and you start talking about the activity of ions rather than just their concentration, that starts to account for some of those factors. Okay, so know that even though we work this mathematics and it seems very nice and clean and systematic, it doesn't always represent reality as much as we would like. Okay, but nonetheless, it's how you work the textbook types of problems. Okay. All right, so that gives you one example problem. Let's move on. Let's try a slightly more challenging one. Question type 2. Can we use a solubility product to predict molar solubility of a compound in which a solution in which a common ion has been added? Now, a common ion, we need to define that first. Okay? That is an ion that's present from a different source than the equilibrium being considered. Okay, so in this previous example, with say the lead iodide, if I would have dumped some potassium iodide in this beaker while this equilibrium is being established, the presence of that potassium iodide could affect this equilibrium. It doesn't matter if this iodide is from this dissolving or from some other source, it affects this equilibrium chemically. Okay, so when we're talking about a common ion, that basically means that we're adding an ion from a different source, and that could have an effect on the equilibrium, and certainly will have an effect on the equilibrium. So to work an example problem like this one, why don't we consider concentration of lead 2 ion, or predicting the concentration of lead 2 ion in a saturated solution of this salt, same salt as before, but now it's going to contain 0.02 moles per liter sodium iodide. Okay? So it's a little bit different situation, because here we're going to have a common ion. When you're faced with this type of problem, don't be scared by it. Just go through your systematic approach. Start by writing the balanced chemical equation. Necessary thing you need to do, okay? Then write your KSP expression. Now this sparingly soluble salt is the same one we used before. We knew the KSP was this. That's just a tabular value to be given in the problem. And that's equal to the ion concentration product with the iodide squared by virtue of this 2 again in the stoichiometry. Same reaction as before. Okay. Then, next step, go to your ice table. A lot of times, students when they get good at this will want to skip writing the ice table. I do not advocate that. I like you to write it out because it's a very systematic approach. If you write things down on a piece of paper, you're less likely to make mistakes and answer things incorrectly. So by all means, write this out. I think it just benefits you. It only takes a couple seconds, okay? But of course, ICE stands for initial change in equilibrium. That's where we get our ICE from. We write the reaction at the top again, just like we did before. Have a series of columns, one for each substance. This one we don't care about because the lead iodide, the solid, doesn't appear in our KSP expression. Consequently, we don't need to track it. We need to write entries for initial concentrations. These are molarities for everything, because whenever you do an ice table, the values you put in the ice table should be molarities, or moles per liter, concentration, okay? That's what we should put in this ice table. Now, do we have an initial standing concentration of lead before any of this dissolves? Remember, that's how I define the initial, before any of the salt dissolves. At least that's like how I like to think about it. And as I read the question, it seems like we have no source of lead. So that's just going to be 0. However, I did note earlier that the solution that I'm dissolving my lead iodide in has a 0.02 moles per liter sodium iodide concentration. Okay, so we have some sodium iodide, and this is a strong electrolyte, dissociates completely, or so we're going to assume breaks up into Na plus ions and I minus ions. If that's the case, we get one copy of that, one copy of that. So the concentration of the iodide is 0.02 moles per liter. That's my initial concentration. Even if none of this dissolves, I still have 0.02 moles per liter iodide from this different source. Okay. Now we're going to assume still that some of this will dissolve. So I'm going to have a positive change and a positive change. I don't know what the change is, so again, I'm going to introduce the variable x and call my change plus x. And if that's plus x, this one's got to be plus 2x. Note when I'm assigning these variables, generally speaking, what I'll do is I'll look at the stoichiometry. And whatever ion makes one copy, I'll call that x, because then it just makes it easy to make this 2x or 3x or whatever is necessary. You don't want to get to a point where you're like x over 2 or something like that. It's just a little bit sloppier. It's not necessarily wrong, it's just a little bit sloppier. It's easier just to do x and 2x, okay? So think about that when you're assigning these variables. And again, third row is equilibrium. You just add whatever's above, so 0 plus x is x, 0.02 plus 2x is what I would expect for that. So when some of this stuff dissolves, I'm going to increase the concentration of lead, and I'm going to increase the concentration of iodide in accordance with these equations, okay? So I think you probably have a pretty good idea for where we're going to go at this point. We're going to take the numbers that we've generated in our ice table for our equilibrium condition or position, and we are going to substitute into our K expression for KSP. Now we learned earlier that the KSP value that governs the dissolution of the lead iodide salt is 7.9 times 10 to the minus 9. Actually a reasonably small KSP, so that stuff is not very soluble. We also learned that that's going to be equal to our ion product the concentration of our ions at equilibrium times each other, but we've got to square the iodide term first, okay? So with that said, I could rewrite this expression as x, which represents my lead concentration, and 0.02 plus 2x squared because that is what represents my iodide concentration. Of course, all these again are the expected equilibrium concentrations. Alright, you see how that works? Alright, so then the next thing I need to do is take this and square it. We do that by that so-called FOIL approach, right, that you learned about in algebra. There's probably a lot of other videos you can look up for that online if you forgot that so-called FOIL, right? First, outer, inner, last type business. If you look it up, you'll be reminded of that. But if you do the multiplication, oops, a short 1 0 here. I'll write that. Sorry, it's a little bit sloppy. Just short of 0 here. We get that as our answer, okay, for the expansion of this term right here. Just squaring it, basically. I can now distribute this x. In doing that, I'll get 4x to the third power plus 0.08 x squared plus 0.0004 x. And that whole thing has got to equal 7.9 times 10 to the minus 9, because that's, of course, our KSP value. Alright, so hopefully that makes a lot of sense to you, what we've come up with right here. Now, if you can solve that equation, if you have a calculator that can help you with that, to find a value of x that you can plug in there and make it work, you're golden. You're off on the right track. However, if I'm looking at this, the solution is a little bit muddled to me. Okay, it's not necessarily clear. If it was a x squared plus an x plus a number, I could use the quadratic equation to solve it without any problem. But this, of course, is x to the third power with an x squared and then an x term, so it's a little bit messier, a little bit more difficult to solve. Not to say it couldn't be solved. You may have methods to solve it, and that would be great. However, it could take a little bit of work. So what I'd like to then sort of teach you about is something that we can use somewhat often. This makes our life easier. It's called the process of making a simplifying assumption in our mathematics. The first thing I want you to know about simplifying assumptions is that it's always mathematically incorrect. Okay, it's always wrong. But the beautiful thing about it is sometimes you're going to be able to ignore certain variables in these equations that we develop. And in doing that, you're not going to change things very much. Okay? It's not going to change the result very much at all. And that's the beautiful thing about the simplifying assumption. So we're essentially going to get still the same answer that we would have otherwise. In making an assumption, it's going to make the mathematics a lot simpler to solve for x. The equations are a lot simpler to solve for x. So it generally is a big savings of time. And that's why we do it. Okay? It just makes our life a little bit easier. Now, how does this process work? Okay? How does it work? So to show what to look for to make an assumption, I want to go back and highlight my ICE table again that we talked about earlier. When you're making an assumption, you want to look for a term that looks like this one in your mathematics. And what stands out to me as characterizing such a term is you've got some number, plus or minus, x or 2x or some variable of x, okay, variable unit of x. The reason why we look for this is as follows. Imagine in your head x is a tiny, tiny, tiny number. I'll take it to extreme. Let's say x is 10 to the minus 15th. Okay, tiny number. If x is 1 times 10 to the minus 15th, if you multiply that by 2 and add it to 0.02, does that really make a difference in this whole result? Not really. This was 0.02, and if you add 2 times 10 to the minus 15th to that, it's still 0.0200000002 and so on, right? So the answer within the parentheses doesn't change very much. So if that's the case, maybe this 2x that I tack on here, or maybe subtract, it could be subtract as well, okay? Same business. Maybe that 2x is just not all that significant. And if that's the case, maybe I could make an assumption that 0.02 plus 2x is approximately equal to 0.02. So that's the assumption I'm going to make here. Now why does that matter? Well, let's rewrite the KSP expression now after making our assumption. So I write my KSP value, that's the tabular value, and I know it's equal to my lead concentration times my iodide concentration. The second one's got to be squared by virtue of the 2 in the ice table, okay? So my lead concentration I already defined in my equilibrium ice table as X. And if I make this assumption, my iodide concentration now becomes 0.02. Now, this is great because I can square this, right? And if I do, I get that. Tack on the x or multiply by x, and now that's equal to my KSP. And then I can solve for x in one division, and I'm done. So the beautiful thing here is, by making an assumption that 0.02 is approximately equal to 0.02 plus 2x, I have drastically simplified the mathematics that I need to carry out. Instead of going through the solution for this equation, I've simplified to this expression, which is easily solvable in a minute or less. But since I have made an assumption, I might want to go back and justify to myself that this assumption was in fact true. Okay? Because sometimes it might not be true. Maybe this is significant to that. Well, we need a standard to help us do this. And the standard that I usually use, I call the 5% rule. Basically what I do is I check whether or not x that I find is bigger or less than 5% of this number. So to do that here, I would take my x value divide it by the 0.02 and multiply by 100 to express it as a percent. And this was 10 to the minus 5 as well. It almost looks like a 3, but it's a 5, okay? So if I round this up to say, make it just a little bit bigger, to 2 times 10 to the minus 5, just so I can kind of estimate here, sort of see what we got, okay? So this is 10 to the minus 2, this is 10 to the minus 5, so it looks like there's a factor of 1,000 difference between these numbers. So if I'm not mistaken here, this term without multiplying should be this. And then if I multiply by 100, I move the decimal place 2 spots. So my x here that I solve for is really only about 1% of that number. So in fact, the dissolution of the lead iodide only produced about 1% more iodide, or about 2% more iodide, than what was already there to begin with. So consequently, since my x was less than 5% of that number, I say my assumption is valid and I will use it. If it's not less than 5%, generally you need to return to this form of the equation, the long form, without the assumption, and just solve it for x. Okay, just numerically solve for x. But that's an example of making simplifying assumptions. We're going to do this quite often. Okay, saves a lot of time if you're able to do it in solving problems. Now, you need to practice a little bit with this to determine whether or not making an assumption is a good idea or a bad idea. Because you don't want to make an assumption and then realize it fails down the road, okay? There are some hints. There are some hints that you can use to determine whether or not it's a good idea or a bad idea to make an assumption. What I'd like you to do is think about what x represents. Here it's the change or the additional amount of this material that dissolves. You have to think about whether or not that's going to be a big number or a small number. Okay? Whether it'll be a big number or a small number. The way to tell that is to look at the k value. Remember, the k value tells you the position of the equilibrium. If k is very small, the equilibrium lies far to the left. If k is bigger, the equilibrium can shift to the right, and more of this stuff will dissolve. This number is quite small. Because of that, I had a pretty good guess that making the assumption is going to work. What I really like to look for, oftentimes, is I'll compare the magnitude of my k with this number right here. If the number I'm adding or subtracting my x term from is greater than, say, 10,000 times larger than what this is, in this case it meets that criteria, then I'm pretty satisfied with making an assumption. I'm pretty confident it's going to work if this number is 10,000 times bigger than this one. And that's kind of just an internal standard that I use to think about when working these problems. Okay? But nonetheless, we've showed an example of a simplifying assumption. We've solved for x. And what does x represent? Well, again, I shift back to my ice table now. And x was 1.98 times 10 to the minus 5. If I want to think about what that represents, it was the concentration at equilibrium of lead 2 plus ion. And if I want to think about the concentration of the I minus ion at equilibrium, I'd solve this equation. I'm going to be a little bit over this, okay? So that's what x represents for me now. And if I go back to the original question, predicting the molar solubility of the compound in this special solvent with the sodium iodide, that molar solubility would be x, because I get one copy of this for every one copy of this that dissolves. So the number of moles per liter of this that can dissolve is 1.8 times 10 to the minus 5, based on the conditions of this particular problem. That would be my molar solubility. At the tail end of this problem, let's consider what happens when a common ion is added, or how does that affect the molar solubility. Well, in this example, where a common ion was present, we saw the molar solubility was about 2 times 10 to the minus 5. What was the molar solubility in the first problem, where only pure water was used? There, it was 1 times 10 to the minus 3. So if we compare the values, 1 times 10 to the minus 3 with 1 times 10 to the minus, or 2 times 10 to the minus 5, we can see that in pure water, the solubility was much, much higher. While in the presence of a common ion, the solubility was significantly reduced. This is a very common effect of a common ion. Generally speaking, you will find the solubility is reduced when a common ion is present. Alternatively, if you add an ion to the mixture, which can use or consume one of the products of the dissolution, that generally increases solubility in an opposite manner. So this video has outlined a review of solubility product constants, shown a couple of example problems of using KSP. It's an important concept. You're going to see problems like this in your homework and on exams, so you should definitely spend some time to review it. I hope you've enjoyed the video. See you next time.